Hello and welcome to this tutorial on using the double integration method for finding deflection in beams. In this tutorial, we are going to solve a simply supported beam with a triangular distributed load. So although the beam is relatively simple to solve, being simply supported, the load adds another layer of complication. Let's have a look at it together. In this example, we consider a simply supported beam AB of uniform cross-section spanning 10 meters and carrying a triangularly distributed load along its entire length. The load intensity increases linearly from 0 at support A to maximum value of 10 kilonewton per meter at support B as shown. Our task is to determine two things. First, the equation of the slope along the beam, and second, the equation of the elastic curve. Because the loading varies continuously across the span, this example is slightly more involved than the uniform load case. However, the overall approach remains the same. We will establish the structural behaviour, write the bending moment expression as a function of position, and then apply the double integration method to obtain slope and deflection. This example is particularly useful for exam prep. It reinforces how to deal with non-uniformly distributed loads within the same framework used for simpler cases. This slide summarizes the procedure for the double integration method, which we'll follow again for this example. We assume that EI is constant along the beam, and we begin by sketching the elastic curve using the boundary conditions to guide the expected shape of deflection. We then use the method of sections to write the bending moment expression mx at an arbitrary distance along the beam. For non-uniform loading, like in this case, this expression will vary with position. The bending moment is then integrated once to obtain the slope equation, and then a second time to obtain the deflection equation, remembering to include the constants of integration. Finally, these constants are evaluated using the boundary conditions at the supports, and the resulting expressions can be used to find slope and deflection at any point along the beam. On this slide, we begin the analysis by following the first steps of the double integration procedure. First, we sketch the elastic curve. The beam is simply supported, so the vertical deflection is 0 at both supports A and B. And under the triangularly distributed load, the deformation is asymmetric, with a larger curvature towards the end where the load intensity is greatest. The sketch reflects the expected behaviour and helps guide the sign of the bending moment and the curvature. We then move on to finding the bending moment equation. To do this, we'll introduce a coordinate x measured from the left-hand support A along the span. Because the load intensity varies with position, the resulting bending moment expression will be a function of x rather than a constant or simple polynomial. Using this coordinate, we'll write the bending moment expression at an arbitrary section of the beam. Before we can do that, we need to determine the support reactions using equilibrium. We'll begin with the horizontal equilibrium, and since there are no horizontal loads acting on the beam, the horizontal reaction at support A is 0, so AX equals 0. Next, we take moments around point A. The triangularly distributed load is represented by an equivalent resultant force. The resultant force is always equal to the area of the load, in this case, the area of a triangle. So in our case, the load itself is 10 times 10 divided by 2, so 50 kilonewtons. The resultant of any distributed load always acts at the centroid of the shape of the load. In this case, a centroid of a triangle. For a load that increases linearly from 0, the centroid is located at a distance of 2/3 L from the left-hand end. And taking moments around A therefore gives us by times 10, and then minus, due to the sign convention, 50, which is the distributed load, times the lever arm of 20 divided by 3. So that is the distance from the centroid of the shape of the triangular shape to point A. And that has to equal 0. Simplifying and solving will give us that By is approximately 33.34 kilonewtons. And finally, we can apply vertical equilibrium, so the sum of all the vertical forces must balance out. So AY plus BY minus the resultant force from the triangular load, which we already established is 50, has to equal 0. And substituting the value of BY, we can obtain that AY equals 50 minus 100 divided by 3, which is 50 divided by 3, and that gives us roughly 16.66 kilonewtons. Now that we have the reactions, we can move on to determine the bending moment expression. On this slide, we derive the bending moment expression using section cut. We consider a general section between A and B, so this analysis applies over the entire span, with x being between 0 and L. Coordinate x is measured from the left-hand support A. We cut the beam at a distance x from A and isolate the left-hand portion. The free body diagram of this section is shown at the bottom of the slide. At the cut section, we introduce the internal shear force V and the bending moment mx. The reaction at A is known and acts upwards, with a magnitude of 16.66 kilonewtons. The distributed load over the length x is triangular, increasing linearly from 0 at A. This means that the load intensity varies with position, and the resultant load on the cut section is equal to the area of the triangle over the length x. The resultant force acts at the centroid of this triangular load. And this means we need to figure out what the height of the triangle is so that we can find the area. So let's focus on the geometry of the triangular load so that we can express the load intensity as a function of position. Because the load varies linearly along the beam, the load intensity at any distance x from the left-hand support depends on the slope of the triangle. To determine this, let's consider a small triangular section shown at the top of the slide. From the geometry, the height of the load at a distance x is notated by h. And using basic trig, we can write that tan the angle alpha equals h over x. And that'll give us that the height of the load at any given point x equals x tan the angle alpha. If we look at the full load diagram, we can find out what that angle is. So over the full 10-meter span, the load increases from 0 to 10 kilonewton per meter. This corresponds with an angle alpha of 45 degrees. Substituting this value gives us that the height at any location x equals x tan 45, and that works out as x. Therefore, at any distance x along the beam, the load intensity is simply equal to x kilonewtons per meter. This expression for h allows us to write the distributed load mathematically and is essential for forming the bending moment expression in the next step. So back to our free body diagram. As we mentioned before, we're looking at the region from A to B with x between 0 and L. Drawing our free body diagram again and knowing what we know about the triangular load, we can write the bending moment equation. So sum of moments at the cut equals 0, and the moment at the cut, m, minus 16.66 times x, so minus the reaction force, plus, due to our sign convention, x times x over 2, so the length x times the intensity of the load x divided by 2, that gives us the triangular shape, that gives us our load, times x over 3. That is the distance from the centroid to the cut. So remember, the centroid is 2/3 and then 1/3 towards the higher intensity. And that has to equal 0. Simplifying this, we obtain that m as a function of x, the moment, equals 16.66x minus x cubed over 6. As noted on this slide, if you are using a mathematical solver like Maple, it is actually best to avoid rounded decimals. So in this case, I would write the reaction force exactly as a fraction, like the 50 over 3x minus x cubed over 6. And that is to avoid any rounding errors. So this is the bending moment expression that we can now integrate to obtain the slope and deflection equations. On this slide, we can carry out the two integrations required by the double integration method. First, we integrate the bending moment expression once to obtain the slope. So in our case, substituting the moment, which was 16.66x minus x cubed over 6, and integrating term by term, gives us the slope expression here with our first constant of integration. So this becomes 8.33x squared minus x to the power of 4 over 24 plus c1. We will then integrate that expression for slope a second time to obtain the deflection equation, and that'll introduce a second constant of integration, c2. So carrying out that integration gives us the deflection expression shown at the bottom of this slide, so 2.776 x cubed minus x to the power of 5 over 120 plus c1 times x plus c2. At this stage, we have the general expressions for slope and deflection in terms of the unknown constants c1 and c2. And we'll determine them next using the boundary conditions at the supports. So let's start off by defining what those boundary conditions are. For a simply supported beam, the vertical deflection at each of the pin supports is 0, and that gives us two boundary conditions. The first one, the deflection when x equals 0, so we're at point A, has to equal 0, and the second one, when we're at x equals L, or we're at point B, the deflection there also has to equal 0. In this example, even though the loading is triangular and the bending moment varies along the span, we still have a continuous region. So these two boundary conditions are sufficient to determine two unknown constants, C1 and C2. We'll substitute them into the deflection equation and solve for the constants. And once they're known, the slope and elastic curve expressions are fully defined. Let's start by applying the first boundary condition. So for a simply supported beam, the deflection at the left-hand support is 0. So y when x equals 0 equals 0. So all we need to do is take the equation for deflection that we already found, the EI times y, and substitute x equals 0 into it. When we do that, all terms that involve powers of x vanish. And this leaves us only the constant term c2, and therefore c2 equals 0. With this boundary condition applied, the deflection expression is simplified to 2.776 x cubed minus x to the power of 5 over 120 plus c1 times x. We can now apply the second boundary condition. So as we said, for a simply supported beam, the vertical deflection at the right-hand support also has to be 0. So when x equals L, the expression EI times y has to equal 0. We'll substitute x equals L into the reduced deflection expression that we obtained on the previous slide. And this gives us an expression only involving the remaining constant C1. At this point, I just want to note an issue with accuracy. So in this example, several of the coefficients were already expressed in decimal form as a result of earlier rounding. Now this is acceptable for hand calculations, but it can lead to accumulated rounding errors as we progress with all this algebra. So after dividing through by L and substituting the span length L equals 10, we obtain a numerical value for the constant. So once again, just to note that the value is correct to the precision used here, but using exact fractions wherever possible is recommended, particularly if we move into working with software like Maple, where we carry results forward into other calculations. But with that in mind, both constants of integration are now determined. So here we have the fully defined expressions for the slope and deflection of the beam. At the top, we have the slope equation written explicitly as y tag, the slope, and divided through by EI to give the physical rotation along the beam. This expression is valid over the entire span. And below that, we have the corresponding expression for the vertical deflection y, again divided by EI. This equation fully describes the elastic curve of the beam under the triangularly distributed load. And this completes the analysis for the simply supported beam with a triangularly distributed load. Thanks for joining me. I hope you found that useful, and I hope you join me again for some more structural engineering.